The first straw bale structures were built over 100 years ago in the sand hills of Nebraska by European settlers. Many of those homes still exist in good shape, as do a few more in other parts of the world where baling machines had appeared over the subsequent decades. 20 years ago, the American West witnessed a revival of interest, initially sporadic and now exploding all over the globe. To date, however, there have been relatively few resources to help architects and engineers design straw bale structures. In responding to the question, how will this building perform, we have relied mostly on intuition and anecdotal evidence. In 2001, the nonprofit Ecological Building Network, or EBNet, received substantial funding from the state of California to conduct the seismic, thermal, and moisture testing needed to address basic questions about straw bale construction. In 2006, the AirShear Foundation provided EBNet funding to complete the final and crucial test, fire. Building codes express the fire safety of walls as a function of fire resistance. This means how long can a conflagration exist on one side of a wall before enough heat is transmitted through the wall to ignite materials on the other side, even if a fire has not actually breached the wall. The American Society of Testing and Materials, or ASTM, full-scale fire test consists of constructing test specimen walls in movable steel frames, allowing the plaster to cure for at least 28 days, moving and clamping the wall specimens up against a furnace with a 10-foot by 10-foot opening, and starting the burners. Over about 20 minutes, the temperature is raised to above 1700 degrees Fahrenheit, and held there or higher for the duration of the time of the test. Immediately afterwards, the specimen is moved away from the furnace to a position where a fire hose can spray the burned surface of the wall so as to apply pressure and verify the structural stability of the specimen. The hose is of sufficient force to knock a man from his feet. Failure of the test would be caused by too much temperature rise on the far side of the wall from the furnace during the burn, or by penetration of the hose stream through the wall specimen. A thick mixture of straw and clay or cob is commonly stuffed into the voids between the stacked bales. This has been shown by experience and lab tests to improve fire and every other kind of performance in the wall. This is wall 1, with a lime cement plaster, being moved by gantry into position at the fire chamber. As very specifically proscribed in the test procedure, thermocouples are attached to the wall in 9 locations spread around the opposite side of the 10-foot by 10-foot fire opening. The temperature reading at any of these points cannot rise by more than 250 degrees Fahrenheit, which never proved to be an issue. The biggest temperature rise was less than 100 degrees. The test begins with the firing of high-intensity gas burners in the chamber, aimed parallel to, not at, the wall surface, as seen here through one of the many glass viewing ports. Within about 20 minutes, the plaster has begun to crack. On the outside, both steam and smoke begin to emerge from cracks. The steam is from moisture in the bales and plaster. The smoke is from the straw charring at the cracked plaster in the chamber. After 2 hours, the burners are shut off, and the wall is unclamped and removed as quickly as possible from the fire chamber. With the release of the clamping pressure, the remaining burnt plaster falls away from the straw, and the sudden rush of oxygen feeds a brief burst of flames. The flames quickly die down, leaving a surface of charred straw to face the hose test. The hosing, like the burning, is very specifically defined by the test protocol, passing back and forth and up and down across the surface of the burnt wall. Some leakage is allowed, but the hose stream itself cannot penetrate at any time during 2.5 minutes of hosing. The difference between the burnt and the unburnt surface is striking. When plaster was removed from the non-burned side, the bulk of the straw was found to be uncharred. This showed that bales behave like heavy timbers in fire, in that the surface will char and then insulate and protect the fibers beneath the surface. For the second wall, a much larger frame, 14 feet by 14 feet, was used simply because that was all the lab had available at the time. These larger frames are for testing load-bearing assemblies and have hydraulic lifts with which to apply a simulated load. 600 pounds per linear foot was applied to the stacked straw before plastering, but because the load was not reapplied just prior to testing, this was not considered a load-bearing test. Again, 15 or 20 minutes into the firing, plaster begins to crack and, to a limited extent, spall inside the fire chamber. The circular images are the burners on the far side of the chamber. The horizontal rods are temperature probes monitoring conditions inside the fire chamber. Again, as the wall is pulled away, burnt plaster falls away, and a brief burst of flame ensues. For the 1-hour test, the hose stream is applied for 1 minute. Note that the burn area, 10 feet by 10 feet, is smaller than the overall wall surface. This gave us a chance to later compare burnt versus unburnt earth plaster. Here, a garden hose is blasting a section of unburnt earthen plaster, which melts away relatively quickly. Then, the hose is pointed at a burnt piece, which shows substantially greater resistance, indicating that the clay in the plaster had partially vitrified. We had expected the walls to pass at least one of these tests, but in both cases the walls performed far better than was expected, and we learned a great deal more about how plastered straw bale walls perform under extreme fire conditions.